For the design question in this week's homework, it asks for the gain from your graphs. And there's actually multiple ways to find that gain. So let's look at, let's say this is V out. Let's say this is V in. Oops, wrong way, since it's inverting. Something like that. So there's two. The first way, which you'll do in lab, but is actually one of the least accurate ways to do it, is you'll find the max and min of V out. Take that difference. So from V out max minus V out min, and that equals your delta V out. And then over here, do the same thing. Make V in min, or max, minus V in min, and that's your delta V in. And you know gain equals your delta V out, your delta V in. From the graphs I've been seeing, that is probably not the way you want to go. For some of you, if you had a pretty good sized V in that you amplified, for your V out, you may have gotten something that looks like this, flat, like that. Okay, so there's a reason for this, and it is that V out can't go higher than your supply voltage. So what this is trying to do, it's if your amplifier has a gain of 100, just as an example, it's trying to multiply this input signal by 100, but that would go very much higher if it was a gain of 100. But just because I don't have a space, we'll say that's what it's trying to draw, but the output can't go higher than your supply voltage or lower than ground. So it gets cut off and it looks like a square wave. It's actually trying to draw this sine wave, but because it can't go above the supply voltage or below ground, you see these flat sections. You see these flat sections here. And they are not actually representative of the gain. So this right here would be representative of the gain. Right, let's see, that's what color shall we use? Purple? Right here and here are representative of the gain. So what you can do is, if you take yellow, I think that'll work, orange, if you see that you're still in a gain region, you can look at your V in signal and say, hey, oh, V in went from here to here. So in that case, that is your delta V in. And then on your output, that to that, that's your delta V out. So instead of going rail to rail, so the first one is just go rail to rail, your V out max minus your V out min over, actually, your V in min. Since when V in is low, V out is high. So ignore this over here. This is actually the negative of the gain right here. V in max is your gain. But if you have any flat spots like this, you're not actually, by taking the maximum of your output, you're not really seeing what the gain is. So the second one is just to take a little segment, just a little segment, and in this little segment, find, let's see, that would be over here actually. On the V in, you find the V, that point on the V in and the point on the V out. That's your V in one and your V out one, and then find your V in two and your V out two, and do the same math, except use points on where you still have a slope on your graph, not in this flat part here. Because this flat part, it's not actually following what the gain is telling it to do. So those are two ways. The third way is to do an AC sweep. And we haven't really talked about AC sweeps. Whoops. AC sweeps, but they are Bode plots. And if you remember, the Bode plot has a magnitude plot. And up here, this is 20 dB of the gain. This top section right here should be 20 log of gain. Okay. So that's 3 ways. There's one more way. I'm blanking on it. Oh, if you do, sorry, last one is if you do a DC sweep. So both of these are the simulation type would be pen stopped working yet again. Still not working. Gonna try to do it with the mouse if the pen stopped working. This would be a transient response. This one also would be a transient response. The third one would be an AC sweep type simulation, and the fourth one is a DC sweep. And remember, if you are doing a VTC, you must use a DC sweep. And you sweep your V in, and you watch your V out. But there's a problem here, because when you your V in is going through a capacitor to your amplifier, and DC sweeps are actually giving DC voltages. And what happens to a capacitor when you have a DC input? Yes, this would, I'm having to draw everything with the mouse now, so. Having a doing a DC sweep means it puts a DC value on here, sees what V out is, then puts a different DC value on here and sees what V out is. So each time you're actually doing a DC simulation, and that means this will be open circuited, and your V in will never get to the input of your amplifier. So what you actually have to do, and it's nice since you have copy and paste, is you have to take your amplifier and do a separate DC sweep here. You have to extract your amplifier from the complete circuit and just do a DC sweep. In this case, it would be 0 to 6 volts. And then hopefully if you don't understand why you can't use a DC sweep when there's a capacitor, an AC coupling capacitor, please come talk to me. But if you do that, then you get your VTC, and double clicking on, up on above your graphs, you always have the label of, double click on that and take 2 points. And notice, because this is a DC sweep on the x-axis, you'll have V in on the x-axis. So if you double click on this and then a little window comes up, gives you some values. Down at the bottom there's slope, and that is your gain right there. So if you do a DC sweep, first of all, you can't use that AC coupling capacitor. You have to take your amplifier, separate it from your circuit, do a DC sweep on it, And the DC sweep, the slope of this line will automatically be your gain for you.